prefabrication, first of all, we know that involves as much off-site construction as possible. And so in prefabrication, we try and do as much building as possible in factories. Because there, our workers can work more efficiently. They've got better access to tools. They're more comfortable. It's just so much quicker if we can build in factories or workshops. Of course, prefabrication implies that there's going to be quite a good transportation system, because almost all of the components have to be transported, usually by truck, to the building site. And once components are at the site, prefabrication requires a high level of craneage. And so the contractors who are doing prefabrication have got to have, very adequate craneage on the site. And that often can be quite a challenge, because it depends how the local contractors are set up to deal with high capacity craneage. When we think of prefabrication of structural elements, we're really talking about simple and quick connections. We want the structural components to be craned into position on the side, and then very, very quickly we want the connections to be made. And so that more or less says that most of the connections need to be pin joints, to be simple and cheap and quick. Then when we think about prefabrication, we've got to consider the degree of its permanence. Is the hospital going to be permanent after the crisis is over, or will it be relocatable? I mean, if prefab structure, excuse me, participants, but some of you need to turn off your microphone, please.
Iya, minta tolong Bapak dan Ibu yang masih menyala mute-nya, yang saya lewati, mungkin bisa bekerja sama dengan turn off. Ya, terima kasih kerjasamanya. Alright.
Yes, so we have to answer the question: is the hospital going to have a permanent life, or are we going to deconstruct it and maybe relocate it? I mean, maybe it could be stored somewhere so that in another crisis in some years' time, it could be erected somewhere else. Because if we want our structure to be relocatable, well, then we have to make sure that it's basically a bolted construction, and everything can be unbolted and rebolted. Then there's the question of the time frame. How long have we got to design and build such a facility? And of course, the longer we've got to build it, I suppose the better the job will be, because we're going to be able to perhaps make the construction more economical, because we won't be putting so much emphasis on speed. So the construction time frame is also important. And finally, I just want to refer you to quite extensive literature on prefabrication. I mean, prefabrication is not a new phenomenon. In fact, it started in as early as the 14th century. Famous kings had their their temporary houses transported with them when they went on battles. And so prefabrication has actually been around for a long time. And I think you would enjoy looking at some of the literature that talks about it. But I'm not going to say any more about that today. So I just want to now mention just 4 aspects of hospital design. And the first aspect is that in hospitals, there are so many functions that we as designers have to accommodate. You know, there are big numbers of staff and different types of staff, doctors, nurses, support staff. And the support staff include, I suppose, administrators through to, you know, technicians, through to maintenance staff. And then there are lots of departments in hospitals. You know, a department for doing triaging or examinations, radiology, pharmacy, laboratory, the wards for the patients, operating theatres, intensive care units, and so on. So, you know, a fully functional hospital is actually, you know, very complex in a number of different departments and different aspects that designers have to consider. And so as a result of that, when we're designing a hospital, we're faced with very complex space planning. And even the circulation can be quite complex because in some places, patients are not allowed. In some places, the public visitors are not allowed. And so the whole of the spatial design of a hospital is very complex. And of course, that's why some architectural practices have sort of specialized in hospital design. And they would have taken a long time to develop their design skills to cope with such complex programs. We then have to remember that hospitals are very highly serviced. They need very significant heating, ventilating, and air conditioning systems. Sometimes they will have rooms that have to have like negative pressure to contain viruses and other organisms to stop them spreading. As well as that, the electrical, water, the gas system, and the data system in a hospital, that'll always be far more complicated than what we encounter in our day-to-day design activities. And then my final comment is just to remind us that in hospitals, all the surfaces are of high quality. You know, they need to be able to be cleaned effectively and frequently, and they need to be able to wear and sustain the use that they're given. So of all the buildings that architects design, I suspect that hospitals would be among the most challenging. And I mean, I haven't even talked about aesthetic aspects of hospitals, but that won't really be mentioned today because we're talking about hospitals in times of crisis. So those are my general comments about prefabrication as a system, and you know, the general comments related to the design of hospitals. And now we move on to just look at just several examples, just to remind ourselves of what is happening in the world around us regarding prefabricated design. And I want to begin by taking you back to Wuhan in China, where we read quite extensively about several hospitals there that were built incredibly quickly. I think this one was built in 10 days. And they had 7,000 workers on the site and working 24 hours a day in 2 or 3 shifts. But just before we look into this building a wee bit more closely, I think we have to say that this actually isn't like a real typical hospital. It doesn't have a lot of the departments and functionality that I mentioned in an earlier slide. Basically, this construction here is to provide accommodation for isolation. I mean, there will be areas where patients are examined and triaged, but basically the rooms are for isolation. And so it's a bit misleading to say that this is like a full hospital. And of course, because it won't have the services of a real hospital, I mean, this is one of the reasons it was able to be constructed so quickly. But nonetheless, what an amazing feat has been for them to design and build this hospital so quickly. So let's just look at a few slides of this hospital, and we'll just talk about some features of it. First of all, we note it's low rise, and of course, the price that is paid is that it's got a very large floor plan. Secondly, you can see the large number of cranes on the site. And during the foundation works, there would have been 20 or 30 diggers and bulldozers. So the whole scale of construction is just beyond what most of us have ever encountered. And then we can begin to see the structural framework of the building. And over on the left-hand side, can you see my cursor, please? Is my cursor visible? Oh, thank you.
Yes, we can.
Thank you. So you can see that the construction of the superstructure has begun by putting down a floor system. And there we can see the floor system. And then the workers erect columns. And in this building, they're all out of structural steel. And the columns have some degree of fixity at their base, like they're able to cantilever vertically. And then having erected the columns, then this floor is craned into position. And look, here is a big stack of floor slabs ready to be craned in. And then, yeah, so, and then what surprised me is that they put in this system, and then immediately over the top of it, they put in another floor system. And so can you see these 2 layers of structure? Now that seems to me very unusual. And maybe this was the price for the speed that was required. Because normally we would never construct having 2, like a ceiling system and a floor system, just sort of one on top of the other. So, you know, that is very unusual. Anyway, and then they build up more columns and put the roofing on. given that it's only a two-story building. Here we see one of the roof systems, the roof system being craned into position and being lowered on to these vertical cantilevered columns. And so in some way, there's enough rigidity in these joints to create a type of frame action to give resistance to wind forces and earthquake forces, because there's no other bracing in this building. Here on the right of the screen, here you can see the double layers. That is so surprising, and I would need more we would need more details to really understand exactly why they might have done that. In other parts of the building, we see them craning down a module, like a self-contained room, really. Maybe this room will house several patients. And this little room has got its own floor system. It's got some steel beams and flooring. And this floor system goes straight on top of this existing platform here that has been craned into position. And then on the right, we see the roof taking shape, and presumably after they've laid all these panels to create the roof, presumably they will cover it with some sort of waterproof membrane to avoid, rainwater leaks in the event of rain. I'm not sure if this is the same site as the other hospital or not. This might be the second prefabricated hospital that was designed and built incredibly quickly. But I show you this slide because here you can see some quite long spans in this part of the hospital complex. I mean, this would be probably between 8 and 10 meters, and maybe this span could be as much as 12 meters. Whereas the previous construction we saw, the module is only of the order of maybe 3 to 6 meters, quite small spans between modules. So this is just to remind us that it is possible to build quickly using prefabrication and have somewhat longer spans. Notice too at this stage that all the structure has been in steel. That is definitely the material of choice for prefabrication. Now I would like us to look at a totally different concept of prefabrication. These images are from a European prefabricated company's website. And the building on the left here is meant to be a hospital building. And on the right is a rather poor floor plan, I'm sorry. And so the hospital is just a two-story building. And what I find interesting about this building is that there's no internal structure. The interior of the building is totally structure-free. And the vertical load-bearing elements, they consist of sandwich, maybe steel sandwich panels with high density polyurethane foam acting as the sandwich filling. And so, in contrast to the Chinese hospitals, a hospital like this is relying on wall panels. They might be about 12 centimeters thick, not that thick. And these wall panels, they are capable of resisting the gravity loads and any horizontal loads from wind and earthquake. I saw some of these, actually some of these hospital buildings are not very strong against earthquake. And in fact, some of them would only have about 1/4 of the strength that one would require in Sulawesi, for example. And so this is a totally different model of prefabrication, not using any columns at all, but it's all about using load-bearing panels. And of course, because the span across the building is so great, it means that the beams spanning have to be quite deep. And from memory, this distance is 13 meters, so that the beams or trusses, they would have to be about 60 centimeters deep at mid-span in order to span 13 meters. Anyway, this type of construction is certainly very lightweight. There's no concrete in the superstructure. And the roof trusses would probably be made out of very thin gauge galvanized steel components. And here is another type of prefabricated hospital structure, just showing the structure, no cladding yet, no roofing. And what I found interesting about this particular one is that all the structural components are aluminium. And of course that rings warning bells to me, because aluminium is quite an expensive metal and it's an expensive material. And so this type of construction, I would think, would be very expensive. But it looks very effective. It's relying on small modules, I think about 2.4 meters here. And it's interesting, they do have some larger spans here, for example, because they're using this truss. And so in this building, they've got perhaps a corridor here and longer spans to create some larger functional modules. This, of course, is only a single-story building, and so the structure is a lot more simple, really. But nonetheless, we would need some rigidity in the joints to make this framework stable, stable against earthquakes and wind. So there we have finished the first couple of sections of my presentation. And now I want to move on to structural considerations. And I want to begin by talking about siting. It's really crucial when we are thinking about providing a hospital that the site is safe. And so it's absolutely essential that we eliminate any risk of tsunami. We've got to make sure that there's no liquefaction that could destroy the hospital or make it not function properly. And also we have to avoid the possibility of lateral spreading. That occurs generally close to water bodies like rivers or lakes, where during an earthquake, the land near the lake or the river, it slides towards the river. We call that lateral spreading. So you definitely don't want to site a hospital near a river, nor do we want to site it where it could be affected by landslides or rock fall. And then we want to check the geological maps to make sure that there are no fault lines running under or very close to the site. Because obviously if there's movement along the fault line and our hospital is built on the fault, the damage will be immense. And what all this means is that before we finalize site selection, we really have got to organize some thorough geotechnical investigations. You know, if we are siting a hospital, we really must get a geotechnical engineer involved, and he or she can check out all the hazards that I've listed and just give us the confidence and the surety that the site that we're building on is going to be totally suitable and not cause any problems to the hospital. So next, I want to talk about the loads that we would design such a prefabricated hospital for. Now, the first three types of load, dead load, live load, and wind load, they are just typical loads that we would design any hospital for, and in fact, any other building for. We might have some areas of a hospital where the live load is heavier than, say, for an office building, because there might be some heavy equipment. But otherwise, all these loads are pretty much what we are used to in normal buildings. But then we come to the seismic load that we must design any hospital for. And I just want to alert you to the fact that typically hospitals must be 80% stronger than normal buildings. And I think you'll see the logic in that. The thinking is that we want hospitals to be operational immediately after an earthquake or any other crisis. And so we must give the hospitals greater strength so that their performance, you know, will be far better than typical buildings nearby. And this means that the structure in hospitals is typically, you know, quite a bit more significant, quite a bit, or the members would be somewhat larger than what we normally see in the average buildings of the same size. And I write the seismic load in red to also highlight to you that you as Indonesian people, and like me living in New Zealand, all of us, we live in a very highly seismically active country. And you particularly live in a very active country, because all these circles, they show the earthquakes in Indonesia for roughly the last 120 years. And you can see how many there are. You are living on a very shaky part of the Earth's crust, as is my own country, New Zealand. We also live on the Pacific Rim of Fire, as does Sumatra and Java and Bali. In Sulawesi, you're not actually on that same sort of tectonic plate line, but nonetheless, look at all the earthquakes that have occurred in Sulawesi in the last 120 years. And so this reminds us that when we're in Indonesia, we have to take earthquake design incredibly seriously. So now that finishes my talk about loads. I want to move on to materials for prefabrication. And so here is a slide showing 4 types of material, and each of these materials is possible to use for prefabricated buildings. We can use wood, you could use bamboo, you could use structural steel and or light gauge galvanized steel, or this could be aluminium if you had a very wealthy client. And don't forget, it's even possible to have precast concrete prefabrication. And that's where I mentioned earlier on, you know, what is the time scale of construction? Because I know in Indonesia, you would much prefer to use precast concrete members than steel members, because steel isn't quite so popular, and possibly you may not have the workers and the skills to do the welding safely. So just going back to that, this choice of material is really incredibly important. You know, what is going to be the material, the structural material for a new prefabricated hospital? Because that will have a huge impact on almost every aspect of the design. And then just at the bottom of the screen, just a query, what non-structural materials are we going to use? You know, what will be the exterior cladding material? What will be the internal partition wall material? What roofing will we design? And so we also, you know, want to think about all the non-structural materials. And as a general principle, because we're talking about an earthquake zone, our material should be as lightweight as possible. Next, just a comment about structural modules. You know, as designers, we have an infinite number of possibilities when it comes to the structural module of a building. And like the two extremes are, first of all, to have the structure, like the columns, uniformly distributed right throughout the building plan. And the spans quite short. Like, you know, this could just be like 2.4 meters or something between these columns. And then we'd have the flooring spanning at right angles. So on one hand, we have this uniformly distributed pattern, and that seems to be the most preferred option for prefabrication, to keep the spans short, to keep the member sizes to the minimum, to make for easy handling, easy craneage. But just to remind you, at the other extreme, we come down the bottom of this slide, and here's the same building plan, and now we've just got 4 columns for the whole building. In other words, 4 really large columns in each of the corners. Now, this would be a ridiculous solution for prefabrication, because these beams here would be so deep because they're spanning so far. And also, we would never want to have a slab of this area, because it would be have to be so thick or deep to span the shorter distance. And so we'd probably have secondary beams running through here. But, you know, these members would be so big, it would be silly to use them in prefabrication, because they'd be so long, they'd be difficult to transport, and they would be very heavy, and they would take an awful lot of fabrication. So to sum up this slide, we probably would say that in prefabricated structures, it's better to think about the structure being uniformly distributed. That would be, I guess, my personal recommendation. And we wouldn't bother with any of these other interesting options. Okay, move on. Still talking about modules, it's just worth remembering the concept of critical functional dimensions. And so each of these shaded modules might represent a ward for patients, or it might represent like a laboratory or an examination room or something like that. Basic functional modules. And so if we have a layout of modules, something like, there are a number of different ways we can provide the structure. And so here on the right-hand side are the options. We could use load-bearing walls. We could use perforated walls. This author calls them eroded load-bearing walls. Or we could use a frame system. I mean, basically, it's either a load-bearing wall or frame system. And so keeping this configuration in mind, we could have load-bearing walls or moment frames running down here. And then we could have flooring going at right angles. Alternatively, we could run our structural system in the other direction, like in the X direction. And so this might be a load-bearing wall or a frame like this in here, and have our flooring and roofing systems going in the Y direction. We could have a two-way system where we have a series of frames, columns, and rigid beams running in both directions. And this is indicating a two-way concrete slab. But in prefabrication, we probably wouldn't want to use cast-in-place concrete, because it just is too time-consuming. And so we'd probably always prefer to use one-way spanning systems. And so these are the considerations that we would bear in mind when we are doing our conceptual structural layouts for a new prefab hospital. Now I want to talk about gravity systems. These are the gravity members that we have in most of our buildings, and I'll just go through them quite quickly. They're post and beam structures. usually with pin joints, top and bottom. And here's a nice example of a primary beam with floor joists or secondary beams running at right angles, and they support the flooring. This is the most simple of all construction types. Then we can have beams and trusses. So here we've got columns creating a moment frame in this direction. This joint looks as if it could be rigid in this direction, but not in the other. And then here we have trusses that could be used in prefabricated buildings, because the trusses can be built in workshops, craned to the site, and quickly erected. And so in the transverse direction, we might have a rigid joint at the base, a fixed joint, and here we might have a rigid joint due to the distance between the truss cords. So in the transverse direction, we've got a series of portal frames or moment frames. And in the longitudinal direction, we've got some cross bracing that no doubt occurs at each end of the building. And don't forget, we can have prefabrication using walls. I mean, I've already talked about using sandwich panels, EPS panels, but here is an example using precast concrete prefabrication. And here, the crane is craning in, wall elements that are load bearing, and then it'll be craning in the slabs. And so, this could be a very good strategy for a job where you had a bit more time. And here's some either walls or floor slabs ready to be craned into position. Very, very fast construction. And here's another a European example using expanded polystyrene sandwich panels. You can just see the way the panels, some are solid, some have openings. And, this sort of system can be erected very, very quickly. And it can be suited for gravity as well as lateral loads. What about flooring systems? Well, in prefabricated buildings, we pretty much want to use one-way floor systems. And so we want to avoid two-way systems that use cast-in-place reinforced concrete. We want to use some sort of precast or steel or wooden joists or secondary beams spanning onto primary elements. So, this A could be suitable if we used precast or floor ribs here, and this would be a system too. But certainly we probably would be avoiding two-way floor systems. What about systems to resist lateral load, like earthquakes? Let me just remind you that when we have a post and beam structure like this, we assume there are pin joints at the bottoms of the posts and the tops of the... And so a post and beam structure is great for vertical, but if there are any horizontal loads, it's actually totally unstable and collapses. And a similar thing happens to load-bearing walls. They're very stable vertically, but if you push a wall out, it'll fall over. And so a load wall can be used to resist vertical loads, but it cannot be used to resist loads at right angles to its length. It needs support in that direction. It's unstable under horizontal load at right angles to its length. Now, when we are designing the configuration of a hospital or any building, we've got to make sure that the hospital can withstand earthquake shaking coming from any direction. And here is like an earthquake pulse at an angle to the main axes of the structure. This is a plan. And so if we want to resist earthquake attack from any direction, we have to provide earthquake strength in the Y direction and the X direction. And so in every building we as designers design, we must always have strength in both directions, in the X and the Y. There are no exceptions. And when we choose the systems to give us the strength, we have a choice of 3 systems. We can use shear walls, we can use braced frames, or we can use moment frames. Those are our choices. And depending on the size of the building, we choose as many elements as possible. And so like here is a simple shear wall building. The shear walls are vertical and they have to be continuous from the foundation beam to the roof. Here's a cross brace frame building, a 1 bay frame in each side. And so, as you can appreciate, a braced frame gets its strength from the triangulation of the members. And braced frames come in different geometries, and any of these geometries we can use in conjunction with discussions with our structural engineer. And finally, we've got the option of using moment frames to resist earthquake. And we just have to make sure that we've got nice strong columns, we've got strong beams, and very importantly, every joint must be very strong and rigid. Only then do we have a proper and strong moment frame. And we have to make sure the columns are orientated properly. Like this is a frame here that's going to resist forces in this direction and only this direction. And so the columns have to be strong in the X direction. This column is wrong because it is weak in the X direction. And so this frame is almost useless. And the same goes for steel. This steel column is strong in the direction of the beam and the frame. That's great. But this column, it is weak in this direction. And so this frame is also almost useless. So we've got to be really careful about the orientation of the columns in our moment frames. Now, finally, what about horizontal elements, floor and roof diaphragms? During an earthquake, the horizontal forces in the earthquake shaking, they are shown on this diagram, which is a cross-section through a building. And in plan, the earthquake forces are shown like this. And they rely on a floor or a roof diaphragm to transfer these forces into the safety of the vertical structure. In this case, it's a structural wall, but it could be something else like a frame or cross bracing. Now, if we have our earthquake resisting structure, say on the perimeter of our building, then the structure is quite discrete. Like in the Y direction, this building is relying on 2 shear walls, here and here. And so we need a strong diaphragm to span between this wall and that wall. Here's another case where we've got in the Y direction a braced frame here and a braced frame here. We need a strong diaphragm spanning the whole length of the building to transfer the forces at each level into the braced frames. In this direction, in the X direction, the span is less and the diaphragm is a lot stronger because it's like very deep. And so it's unlikely we'd have a problem in the X direction. But if the lateral load structure is distributed throughout the plan of the building, and like here's an example where I'm using shear walls to resist earthquake, and I've used lots of them, but each of them is quite small compared to the other cases previously. If we have distributed structure in plan, then the diaphragm doesn't have far to span. It only needs to span between each wall. And therefore, the diaphragm doesn't need to be very strong. But we need lots of horizontal ties to tie all the building together so that during an earthquake, the building doesn't sort of shake to pieces. It doesn't fall apart, if you get what I mean. Here's another example of using distributed structure. In this case, using lots of single bay moment frames. And because the frames are distributed throughout the plan, it means that, the diaphragm, once again, does not need to be strong. Now, in these particular drawings I'm showing you, I haven't shown you the columns that just resist the gravity loads. I mean, obviously there'd be a column in the corner of the building and be lots of other columns, but I haven't shown those. I'm just showing you the structure needed to resist wind and earthquake. And so the big question for all of us designers is how much vertical structure do you need? How many shear walls do you need? And how long do they have to be? So I'd like you to take a photograph of this slide. Just take a photograph with your cell phone, because that's the link that you can go to download incredibly user-friendly software to help you do a preliminary design against earthquake. So there we are. That's the end of my presentation. And so I'm going to stop now. And I guess we're going to have a period of questions and comments. So thank you all very much for your attention. I hope I've been able to be clear to you. So thank you.
All right. Thank you very much, Prof. Andrew, for so insight and new knowledge for us, especially about modular system in hospital. Can you hear me, Prof. Andrew, so far? Just testing.
Yes, thank you. Yes, thank you.
All right. So we are moving to question sessions. There are 2 sessions. First session takes about, let me check, about 15 minutes. Second one is, let's see if we can adjust for the second one. So the form of question is through chatting. So please leave your questions over chatting. the first come is the first serve. Another thing is if we run off the time and we cannot respond your chatting, then if you don't mind, Prof, we will forward email so you can respond to other questions that have not responded through this webinar. Is that okay for you?
Yeah, that's fine.
Okay, so I will read the questions, translate into the English, and I will ask also the participant whether I have to translate for the questions for your response or not.
Okay.
Bapak dan Ibu, ya. Alright. So let me back to Indonesian language. So Bapak dan Ibu silahkan untuk pertanyaan sesi pertama di apa namanya di posting di chatting dan saya akan bacakan ke Pak Andrew dan langsung dijawab. So the first question, Prof, is from Ayada. So she asking that is there any international standard construction for hospital constructions which is meet the standard of 80% stronger than modern building to resistance to the earthquake?
Thank you. That's a really good question. What you find is that if you look into the earthquake codes of practice in most countries in the world, they require hospitals and police stations and fire stations to be designed to a far higher standard. And so in Indonesia, you have your own earthquake design code. I think it's quite new. I think it might be about 2 or 3 years old. And I'm certain that if you look at that earthquake code and if you follow it, you will have to design a hospital to be a lot stronger than a normal building. So the requirement is situated, it is found in your national earthquake code.
Okay, let me translate for a bit if you don't mind. So, Ibu Mayada, Prof. Hendro mengatakan bahwa untuk standar itu akan tergantung kepada code masing-masing negara yang berbasis pada seberapa besar kekuatan atau potensi earthquake yang mereka bisa record. Jadi tidak ada standar internasional, kembali kepada standar nasional masing-masing yang didasarkan pada potensi bencana potensi kekuatan gempa. Yeah. Alright, any questions so far? Do we still have more time? Ada yang masih mau bertanya, Bapak Ibu? Untuk Pak Jos Timotius Runtulalo, boleh di chatting. Pak Jos. Okay, here we go. The second one. Second one is from Mr. Rahid. It seems like he is an architect. There are two questions for you. Are you ready for that?
Yes, thank you.
The first one is there any principle of beam concept that can be applied in the prefabricated building?
Could you please read that question again rather slowly, because I couldn't hear.
Okay, I will read again. Wait a minute, I'll type other, sorry. Is there any principle for column and beam concept that can be applied in the prefabricated buildings?
No, there's no definitive approach that is recommended. I guess we saw in that Wuhan hospital, all the columns and beams are of structural steel, and they've got sort of rigid joints as part of the construction process. So there's no one way of designing structure. Each building has to be considered from first principles, really.
Oke, untuk pertanyaan pertama Pak Afif, tidak ada prinsip yang kaku untuk itu. Nanti tergantung kepada seperti yang dijelaskan tadi, kondisi site, kondisi material yang ada, kemudian perhitungan struktur dan seterusnya. The second one is, so what conditions determine us to choose to use a steel column structure or load the bearing panel?
Well, it depends on economy. It depends on what your contractor's skills are. It depends on what materials are readily available in your own local community. And like it depends on the situation. I mean, if you just want a hospital for say a small village area, then you might make the whole hospital out of plywood and wood. So it depends on the scale of construction, and this is where the architect has to think carefully about the possibilities of each material.
All right, I'm translating for that. So Pak Hip dan kawan-kawan, tergantung kepada ekonomi, skala bangunan, kondisi material lokal. Prinsipnya bagaimana arsitek bisa merespon dengan kondisi yang tadi kami sebut di atas, yang kita sebut di atas. Jadi disesuaikan dengan kondisi lapangan, kondisi konteks sosial, ekonomi. Sebagai contoh tadi, bahkan untuk misalnya rumah fabrikasi untuk rumah sakit yang harus segera dibangun untuk merespon bencana, itu malah bisa dari misalnya untuk komunitas yang kecil, itu bisa dari wood atau dari panel wood gitu. Oke, we move to the third. I think we don't have to make any sessions. I just move until the time is over. So the third one is from Mr. Jos Timotius Runtulano, Pak Jos. His question is, how about substructure about the prefabricated hospital building? So he asking about the substructure.
Okay. Well, for the Wuhan hospital, the structure is very, very simple because the soil conditions were quite good soil conditions. And so all they did was to level the construction site, put down some waterproof membranes, and then cast a reinforced concrete slab over the whole site. So you couldn't have a more simple substructure. It's just a simple reinforced concrete slab. And of course, that is okay because the superstructure is very lightweight. You know, it's only 2 stories high, and the spacing between the columns is quite short. And so you can use a very simple, cheap, and effective substructure.
Oke, ini yang saya mengerti Pak ya. Tadi mudah-mudahan tidak salah. Jadi untuk substructure itu tidak seperti bangunan konvensional biasa, bisa digunakan sekedar material ringan untuk menutupi. Karena pada prinsipnya superstruktur yang digunakan itu light atau ringan. Seperti misalnya contoh di Wuhan, mereka hanya menggunakan panel untuk substruktur karena dengan asumsi bahwa superstrukturnya sudah ringan. We move to other response from Ibu Dewi. So she says that, sorry. She said, thank you, Prof, for your good presentation. And then, wait a minute. Okay. All right. So Ibu Dewi, Mrs. Dewi asking that since we, I mean maybe the Indonesians, we live in the shaky country, do you think this prefabricated hospital still possible to be built and used safely? If so, can I conclude that it will depend on the joints?
Well, first of all, absolutely, you can design a safe prefabricated hospital, but you've got to follow the principles, that I outlined. But if the earthquake forces are designed for safely and carefully, yes, absolutely. A prefabricated hospital is totally feasible in Indonesia. But
Okay.
perhaps I'll just say something that, I mean, because you live in a shaky country, the and the detailing and the connections are going to be a bit more difficult if your hospital was built in a country without earthquakes.
Oke, Ibu Dewi, yang saya mengerti tadi dari Pak Andrew adalah mungkin untuk itu sangat mungkin. Yang penting mengikuti standar yang berlaku yang dipersyaratkan oleh daerah di mana kita membangun, misalnya di Indonesia, yang berdasar pada kondisi konteks lapangan. Kemudian untuk detail desain, jadi Pak Andrew mengatakan bahwa itu sangat mungkin. Yang penting ada usaha keras untuk membuat detail untuk itu, dan setiap kondisi lapangan mempengaruhi kondisi atau desain dari prefabrikasi, termasuk join. Okay, next so we still have more, but I think if I calculate the time, we still can accommodate 2 participants, Prof. Andrew. So the second from the last is from Pak Edi. Let me try to translate first. So Pak Edi asking whether we can use the panel for the wall, and is there any standardization and any specific material that can be used for the panel for the building for fabrication?
Yeah, okay. Well, there's a very wide range of materials you can use. If you wanted to, for a lightweight building, you could use plywood panels, or you could use the expanded polystyrene sandwich panels that they do in Europe. Or if you wanted to, you could use precast concrete wall panels. So all of these panel types are possible.
Okay, how about the weather? Responding weather of the panel, he asking.
Beg your pardon?
He asking how about the panel resistance to the weather?
Well, well, it depends if you want to put an exterior cladding over the structural panel. And like if you put an exterior cladding, you can panel system. But if you don't want to put an exterior cladding, I mean probably a aluminium EPS panel, you know, would be good because it's totally waterproof. Also, you could use precast concrete panels because they can be waterproof as well.
Oke, Pak Edi, jadi beberapa material bisa digunakan tergantung kondisi lagi, misalnya plywood bisa menggunakan juga precast, material yang ringan, atau seperti di Eropa tadi kalau nggak salah material karbonat gitu. Sedangkan untuk tahan terhadap cuaca yang dibuat prefabrikasi itu sudah diperhitungkan untuk itu. Sedangkan material yang misalnya tidak difabrikasi, tapi misalnya dari plywood yang kita buat sendiri itu mungkin perlu penanganan khusus, misalnya waterproof paint kita pakai seperti itu, Pak Edi. Yang terakhir, the last one is from Ibu Marwati, Miss Marwati. So she's asking, in your opinion, which is the best column model system or wall system to anticipate an earthquake? Is that clear?
Yes. Yes, well, if we're using columns to resist earthquake, that means we're using moment frames. And so that means that you must have rigid joints between the ends of the beams and the tops of the columns. And the problem is that if you are using structural steel to do that, I don't know if in Indonesia at the moment you have good enough quality control to be confident that the welding is of an adequate standard to survive earthquake shaking. So my opinion is that if at all possible, you should try and resist earthquakes using walls. And because that seems to be a more reliable way of resisting earthquake shaking. And of course, that means you need walls in both directions because the earthquake attacks from every direction.
Oke, Ibu Marwati, mungkin tadi sudah jelas, saya cuma memberikan sedikit persepsi dari yang tadi Prof. Andrew sampaikan, bahwa prinsipnya strukturnya nggak boleh rigid atau terlalu kaku, tapi fleksibel dengan melihat konteks lapangan, baik material maupun kondisi struktur yang ada di lapangan. Okay, so Prof. Andrew, hello?
Yes, hello.
Yeah, Prof. Andrew, I think there will be left more questions, but as I informed in the early of this webinar that the rest of the questions that have to be responded will be pulled and will be email to you, whether you have a time to respond for that. We appreciate for that. So can I say some information to some participant in Indonesia and before I back to you?
Could I just suggest that they send the questions to you and then you send them to me in one email and then I answer them. And then they can see, everybody can see my answers to all the questions.
All right, yeah, that's what I mean. Sorry, I have not mentioned about that.
Okay.
Yeah, they will pull on me and then we will distribute to you and then we will send back your response for that.
Okay.
So, if you don't mind, I will back to participant for closing statement before I back to you for the closing one. Is that okay?
That's fine. Thank you.
Alright. Oke, Bapak dan Ibu, terima kasih banyak. Mungkin kita sudah masuk di sesi terakhir. Saya ambil beberapa kesimpulan tadi. Yang pertama bahwa struktur prefabrikasi untuk rumah sakit merespon bencana, termasuk mungkin pandemik yang sedang terjadi sekarang, itu sangat tergantung kepada beberapa faktor. Misalnya pertimbangan site, pertimbangan struktur, pertimbangan material yang ada di lapangan, dan beberapa detail yang setelah dijelaskan sebelumnya. Kesimpulan yang tadi saya tangkap bahwa seorang perencana arsitek itu dalam merespon desain ketika mendapatkan pekerjaan atau tugas membuat rumah sakit yang bersifat prefabrikasi itu harus punya pengetahuan yang cukup lebih dan cukup kreatif dalam melakukan proses and output design. Bagi contoh tadi misalnya dikatakan bahwa rumah sakit itu prefabrikasi misalnya itu minimal harus 80% lebih kuat dibanding yang bangunan yang umumnya, karena dia bersifat pelayanan kepada masyarakat ketika bencana terjadi yang harus segera difungsikan ketika bencana sedang terjadi atau setelah terjadi. Demikian Bapak dan Ibu, kami atas nama jurusan arsitektur Universitas Islam Negeri Makassar mengucapkan banyak terima kasih atas kesempatan waktu dan Ibu dan Bapak. Kami mohon maaf sebesarnya kalau di dalam pelaksanaan ini ada masalah teknikal atau ada delay atau semacamnya, mohon dimaafkan untuk itu. Mudah-mudahan respon Bapak dan Ibu di survei itu akan sangat membantu untuk pelaksanaan berikutnya. Ini adalah pertama kali untuk kami, sehingga kami akan terus memperbaiki proses-proses ke depannya. Informasi kami ulang kembali bahwa link survei akan dikirim ke email Ibu dan Bapak. Mohon diisi sebagai syarat untuk kami mengirimkan sertifikat elektronik sertifikatnya. Kemudian kami akan kirimkan email sertifikatnya itu 1 minggu dari sekarang menurut informasi dari panitia. Sehingga kemudian ada hal yang misalnya ingin dipertanyakan, silakan email ke panitia. Oh ya, sebelum saya tutup, tadi ada yang bertanya bagaimana dengan materialnya. Tadi nanti kami kirim juga di email masing-masing, di mana bisa di-download di Google Drive. Ibu, Bapak, saya kembali dulu ke Prof. Andrew. Prof. Andrew, can you listen?
Yes,
can you hear me?
Yes, I can hear you, and I can understand mostly too.
Oh, good. Nice one. Bapak, bila boleh saya atas nama Ibu dan Bapak, kami mengucapkan terima kasih kepada Prof. Andrew. Prof. Andrew, on behalf of participant, on behalf of our faculty, on behalf of our department, we would like to deliver our high appreciation, our deep thank you for your time, your sharing knowledge, and we hope that if this pandemic situation will be over, then you have a time to come and to visit us again. So thank you very much, Prof. Andrew. Stay healthy and keep involved and us. And Ibu dan Bapak, terima kasih banyak.
Pak Fahmi, tapi dulu bisa.
Ya, silakan. Ya, Prof. Andrew, there is for our department here of the department will say something to you. Over to you.
Ya, ini Pak Fahmi bisa disampaikan ke peserta untuk aktifkan kameranya supaya bisa di screenshot.
Oke, Bapak dan Ibu, tadi ada permintaan dari panitia, apakah boleh on-kan videonya untuk kami ambilkan screenshot, katanya photo session itu. So, Prof. Andrew, we told to the participant to turn on the video so we can take the photo session over the screenshot. The new style, new normal style. Okay. Let me check. Oke, sudah selesai. Oke,
Betul.
sekali lagi terima kasih banyak. Ya. Gimana Pak? Pak Sul?
Oke.
Sudah Pak?
Iya, makasih Pak Amin. Makasih
Oke,
Pak.
terima kasih banyak. Oke, terima kasih sekali lagi. Terima kasih dengan Ibu, Bapak dan Ibu waktunya. Selamat menjalankan ibadah puasa bagi yang menjalankan. Sampai ketemu di event berikutnya. Prof. Andrew, again, thank you very much. We appreciate for that. And we will keep contact you after this one.
Thank you.
Yeah.
Thank you.
Thank you Prof. Andrew.
Thank you,
It's been a
Prof.
pleasure. Goodbye.
Bye.
Thank you, Prof.
Goodbye, everybody. Bye-bye.
Thank you so much.
Yeah.
Thank you, Prof.
It's a pleasure.
Oh,
Goodbye, everybody.
yes.
Bye-bye. Hope to see you again one day.
Prof.